for the rest of the labs or assignments, maybe other than the very last one, I'm not sure yet, we're going to be using a new skill looking at contour lines on topographic maps. And I'm sorry, this is kind of a funky view, but I've got some other things I want to show you, so I've set this up where you see kind of the whole PowerPoint here. So what we're talking about is being able to look at the three-dimensional aspect of the surface. So we've been looking at X and Y coordinates, the latitude and the longitude. This is considered the Z coordinate or the elevation. And so if you're using a GPS unit, you will see your elevation value is often identified as the Z value. And so we can talk about the idea of relief. So when I look around my neighborhood, the relief is the difference in elevation between Skinner Butte and the valley floor where I live. And so that difference might be, I wonder if I can get this whole thing up. Nope. There we go. So I think it's like 664 feet down to 400 feet. So that difference in elevation is considered my relief. If I look at all of Oregon, I'm looking at the difference between sea level, which is 0, and I think Mount Hood is our highest elevation in Oregon. So that would be the relief for the state. So relief is a relative term based on the difference in elevation, a high point to a low point from where you are. And so we use relief and elevation in so many aspects of just finding our way around or wayfinding. You use that all the time to establish position. When you're in a new place, you look for, a tall hill, and that lets you know if you're going toward the hill or if the hill's on the right or the hill's west of you. It helps you establish position. If you're doing any kind of orienteering, using maps and compasses to find your way around in the environment, you're using high points and low points to establish your position there. In this class, we're going to use them to distinguish between different kinds of landforms. We're not going to do it for volcanoes, but by using a topographic map, you can distinguish between a shield volcano, a composite volcano, and a cinder cone. We're going to look at a cinder cone in a little bit. You can also identify the differences between a translational slide and a rotational slide or a slump. And if you want to build a house, you may want to look at a river and see which way is the river flowing and which side of the river is eroding, and topographic maps will really help with that. Now, one of the things that's changing is there's so much available with aerial imagery that often helps with that. But with aerial imagery, I don't get a number. I don't get to know exactly how tall that building is or that mountaintop is. I just can see that it's higher than the area around it. If you're going into any kind of science field, looking at resource management or city planning, the idea of elevation is used to understand stream flow, stormwater flow. Portland right now has realized that with global climate change predictions and increased rainwater in the Northwest, their storm system is not big enough to handle the expected runoff. If you're going into any business that's trying to site solar panels or wind panels or water hydroelectric power, you need to know elevation. So this is an important concept for most science kinds of fields. So we've talked about absolute and relative location. You can also have absolute and relative relief. So relative relief just gives me a shading or the perception of change in elevation. Absolute relief gives me a number, how much elevation change, or what is the actual elevation where I am. And many of you, if you've walked around the world, you may have seen these brass caps. They're used for surveying and to provide information about location and elevation, and usually they're fairly accurate elevation markers. So this one is U.S. Geological Survey benchmark, and on a map you'll see that identified as BM with an X on that, and a benchmark means you could find that little brass cap if you were on the landscape. And it says it's 717 feet, and the assumption is above sea level. So when we're looking at a map, a topographic map, you're going to see lines on this map, and you're going to see often indicators of elevation. So right here, this BM stands for benchmark 241. The assumption is feet here. At the bottom of most maps, it will tell you what the units are, and I will always give you that on an assignment, so we won't always have a whole map to work with. Here is what's called a spot elevation. With this one, the benchmark, you should be able to go out on the landscape and find that brass marker. With a spot elevation, this is not indicated anywhere on the landscape, but it is on the map, so you know that that's 220 feet. That's where the X is. The other thing on maps you'll find are what are called ISO lines, and these are lines on the map that indicate continuous values. So we looked at ISO lines earlier in the term when we talked about air pressure and high pressure and low pressure systems, and those were called isobars. Now we're going to be looking at contour lines that show lines of elevation change. So there's the barometric pressure, and I guess I'm not getting there yet. So anyway, how do they know how to make contour lines? So in the olden days, surveyors would go out and they would take an area and do spot elevation. And so they would find these spots and they would make elevation points for each of those spots. So here's sea level right there, and there's 32 feet, 38 feet, 45 feet, 47 feet, and then it goes down to 40 feet, 15 feet. So there's the highest point that they found. And then what a cartographer would do would begin to connect the dots or extrapolate, kind of average between these points to make a continuous line of elevation. So, for example, theoretically, if you were standing on this 30 line, you should be able to walk at 30 feet above sea level in a continuous circle and never change, never go uphill or downhill. You would be just at 30 feet above sea level. Here is the 40-foot contour. So here you should be able to walk along this contour line at 40 feet above sea level, never go up or never go down. And so the difference between the 30-foot contour line and the 40-foot contour line is 10 feet difference. And so when all of the lines are connected, you have an island. So here is an island showing the sea level along the edge of the island. Then there's 10 feet in elevation, 20 feet, 30 feet, and 40 feet in elevation. And so what we say here is the change between contour lines is the contour interval, or 10 feet. So contour lines are really a key to understanding the shape of the landforms. So if I look at this little island here in profile, here is the 0-degree contour line at sea level, and this contour interval, CL, is 500 feet. So there's 500 feet above sea level, 1,000 feet above sea level, 1,500 feet above sea level, 2,000 feet above sea level, and hopefully at the very top of that little mountain there would be a spot elevation or a benchmark that gives me the exact elevation. Unless I have a spot elevation, I don't know what that top of that mountain is. I just know that it's greater than 2,000 feet and less than 2,500 feet. So let's look at it as you would see it on a topographic map. And so here you see this little top of that mountain. There's the 39.98 foot peak, and then there's the lower peak. So what do you notice about the spacing of these contour lines? You're absolutely right. They are not even. So if I go back to this profile, I can see that this slope is kind of more gentle than this side of the mountain. So if I get shipwrecked and I have to climb up to the top, I'm going to hopefully climb up this side, which is less steep because those lines are far apart. So what that's showing you is that there's a lot of distance between the changes in elevation. Here, the lines are really close together, which means this is a steeper side of the island. And so the change in elevation is very rapid, so a steep slope. So from just contour lines and their closeness, you can tell where a steep side is, where a more gentle slope is. And here's another profile example where I'm showing an elevation profile here, where this is kind of a more gentle slope. There's a lot of space, more area, more linear distance if I'm climbing up the side of that mountain than there is here. Look how much closer these changes are. Google Earth is really lovely because it will show you that profile. So here is the top of Mount Hood, and this is climbing from that slope up to the top. You can see here those contour lines are farther apart, but right here those lines get much closer together, so it's more steep. Again, this is Stony Mountain somewhere. I don't know where. Oh, Banff. Okay. And you can see there's a little mountain here. There's that mountain. And then I go through a flat valley, which is all of this. And then I'm starting to climb up this mountain. I'm going down that little valley here and going up the other upper mountain. And it shows me my contour or my elevation change. Specifically, so you need to remember that contour lines show lines of equal elevation, and they are complete circles. So even though the map doesn't show the extent of this 11,000 foot contour, if I were to continue on the next map, that would continue also. So the contour interval is that change, and so for this map, between 10,600 feet and 10,800 feet, each of those lines is 50 feet in elevation. 10,650, 10,700, 10,007. Oh, I might be wrong on that one. Let me count those again. 200 feet. 1, 2, 3, 4, 5. 5 goes into 200. Oh my gosh, hold on, I have to stop. Whoops. It's 40 foot contour interval. You don't count the lines, you count the spaces. So there are 5 spaces between these two. There's 200 feet, so 200 divided by 5 is 40. Yeah, I love these demos. Some other things that you can kind of generally interpret from a topo map is that these lobes or the curvier, gentler turns in a topo map often point downslope. And this is nice when I don't know, when not all of the elevation lines are marked. So here's a 3,000 foot contour. And I don't know if this is downhill or uphill. So sometimes looking at those curves can help me get a general sense. And on this one, I see kind of a road and a stream. So my assumption would be this is lower than that. The other thing is that the little points, or the V's, often point uphill. If we go back to, let's go back to that island profile here. If you look at this, you can see those streams are running downhill, but you can see those little curves, kind of little nick points or little uphill arrows that point upstream with contour lines. And so those help you kind of get a sense of what those lines look like. And then sometimes you can get maps that have contour lines, which are absolute relief, plus shading, which would be relative relief. And the relative relief really helps you visualize the steepness of that slope. So I want to open up this cinder cone. And this is Pistol Butte. It's in Oregon. It's near Lava Butte, and it's the Pistol Butte Lookout. And you can see that these contour lines are very close together. This is the 4,300 foot contour line. The next one that's indicated is 4,500 foot. So you could, let's see, that's these special lines are called the index lines. So the index lines are bolder and they show the elevation. So that helps you have a clue about what this is. So there are, this is the index line for 4,300. And there's another index line, and another index line, and another index line. So I've got 1, 2, 3, 4 spaces of index lines between 430 and 450, 4,500. So there's 200 feet in elevation here. So each of these contour lines has to be 50 feet of contour, 50-foot contour interval. So I have 4 index spaces between these. So 200 divided by 4 means that each of these is 50 feet. And there are 5 of those, so each of those index lines is 10 feet. So let's look at this on Google Earth. So you can see this is a gentle slope. Those lines are far apart. Man, this is pretty steep side. This is a little more gentle, but it's getting pretty steep as you get to the top. So if we want to open up Google Earth, which is, where did I put Google Earth? Let's take a look at Google Earth. I know it's up here. Oh, there it is. Okay, so here is the butte in Google Earth. So you can see that's Pistol Butte with the Sitka Butte in the background, and I could draw a profile line across this butte. I'm going to come out here on the flat, and I'm going to go up over the butte. I went over the back side of the butte. So that's the elevation profile here. And you can see I'm at 4,278 feet. Kind of at the top of the butte is about 5,093 feet. This is much steeper right here. And then it flattens out again. So if we go back to look at this, you can see we kind of went up this side and then over that little bump and back down onto the flat. So using the topographic map in ArcGIS Online, you can read different elevations and talk about the relief. So if I asked you, here is a spot. Oh man, I went in too far. These are somewhat scaled, so if you zoom in too much, they won't show you. So if I'm zoomed way out, I don't see as many contour lines. So I'm going to zoom in here and I'm going to say the top of Pistol Butte, I see a triangle that has a spot elevation, is 5,151 feet. And then I could say the base of Lookout of Pistol Butte is around 4,250 feet. And so the difference in that would be the relative relief of this area. So we'll do a little practice. You can see that Sitka Butte is flat on the top. I might ask you which side is steeper based on the contour lines, whether it's the southeast side of the butte or the northwest side of the butte. And you could support that the southeast side of the butte is a little gentler, at least up until you get to the very top, because the contour lines are farther apart. This face is probably the steepest because the contour lines are closer together. So the first time we do this, we're just going to be able to determine the elevation and to look at the different contour values. Now, I'm using the U.S. topographic map for this, and it zooms in and then you lose because you're in too far. So it has two different resolutions. One is pretty zoomed out, you don't have a lot of detail, and then when you zoom in you get higher detail here. The other base map that you may want to use, and I think actually a couple of them I have used this, has a different contour interval. And so let's see if I can go to, let's go to Pistol Butte. There we go. Oh man, where is it? Oh, right there. Okay. So I'm going to zoom into Pistol Butte. Here we go, here we go, here we go. And turn that off. And so with Pistol Butte, okay, there's 4,400 feet, there's 4,800 feet. And so 1, 2, 3, 4, 5 contour lines and 200 feet. So each of these is 40 feet. I hope I did the math right. We could just check it here. It would be so embarrassing. That's like third grade math. So I had 200 feet divided by 5 contour. Okay, the contour interval here is 40 feet. So I will give you, in the beginning, give you the contour interval, and then you'll need to determine that. This one has shaded relief, so it kind of shows you that 3D perspective. With this little landform here, you can tell that that looks a little steeper, even though the contour lines aren't much closer together, but part of that is because they don't have the really detailed contour lines. So my recommendation would be to go between the two and really get a look at, man, too far, too far. Get a look at that. Okay, so more than you probably ever wanted to know about contour lines, but they're